Hi, I'm Jonathan Pedraza. This is the Distributed Electric Propulsion Senior Design Team at UCF, Team Black. The objectives and requirements of our project is to design a DEP UAV with a minimum wingspan of 36 inches. We just have to get up in the air, fly, and come back down and land.
Hello, my name is Derrick Var, and this is DEP Team Black. DEP proposes an alternative to turbine engines and gas-powered aircrafts. DEP involves propellers along the leading edge of the wingspan, and this is distributed throughout the wingspan, thus creating more lift and a higher lift coefficient. Major benefits include sustainability, which is at the forefront of environmental protection, and a huge reduction in noise pollution compared to the traditional gas-powered aircrafts. In addition to environmental benefits, DEP also provides higher efficiency and performance, as well as design flexibility, which will be discussed further along this presentation.
Hi, my name is Mettler, and I was responsible for the production management and the stability analysis of the DEP aircraft. Prior to getting the project started, we had to come up with a functional and decomposition breakdown to be able to understand our project fully. We had to compare it with a list of requirements needed by both the school and by our sponsor. That list of requirements turned into a production schedule and a Gantt chart where we were able to break down the entire production process, put across our entire 2 semesters.
Hi, my name is Inastrilla, and I am in charge of the propulsion systems section of our project. The first requirement that was set was the thrust to weight ratio of 0.8 to 1. Our plane's weight was 5 pounds, so from there we were able to get a thrust of 4 pounds for takeoff. The first step was to analyze which propellers were going to be chosen for our project. We're using 4 high lift and 2 cruise.
My name is Luiz, and I was responsible for the aerodynamic portion of the senior design project. During the aerodynamic portion of this project, a lot of things had to be taken into consideration when doing the design of primarily the wing and the tail. For our flight conditions, we did a study with different airfoils. The main model that we used to base our research on was the Maxwell X-57 by NASA. One main setback that we had was once we had the different aspect ratios taken into account based on different designs, which was primarily used in the industry for different DEP concepts. However, when we actually put together the dimensions, we noticed that the wing thickness would not be sufficient to generate enough lift. Therefore, many appropriations were needed to be done, and we took a step into decreasing the aspect ratio to account for this geometric loss. During our selection process, the selected airfoil was NACA 5415, and the aspect ratio we came up with was 6. With the selected aspect ratio, we came up with the wingspan of 4.5 feet. For the tail design, the team chose the airfoil of NACA 0012 to maintain simplicity and symmetry. For the vertical stabilizer, we chose a taper ratio as shown on the screen. For the horizontal stabilizer, it was not tapered, and the dimensions of the control surfaces were all based on factor of safety of 1.5.
I was in charge of the CAD design and additive manufacturing portion of the project. A majority of the CAD was done in Fusion 360. We took advantage of the generative design available within the student package, as you can see here.
We began to use different analysis tools. So the first one was J-Blade. It's an XFLR5 tool that's custom built for propellers. It's able to analyze propellers using CFD calculations. From there, we were able to see, we chose different propellers to analyze. So we chose 6x2, 6 meaning 6-inch diameter, 2 meaning 2-inch pitch. We used 6x2, 6x3, 8x4, and 8x3. And from different analysis of thrust and propeller advance ratios, power and propeller advance ratios, velocity, we were able to find that the 8x4 propeller is the most efficient for the cruise motors, and we were able to find that the 6x2 propellers are the most efficient for the high lift. It's more desirable to have a finer pitch for high lift. For the high lift motors, it's more desirable to have a lower pitch and higher RPMs, and for the cruise motors, it's more desirable to have a higher pitch and lower RPMs. Then our next step was to find which motors we were going to choose for our project. What I did was I found the torque needed to run the propellers at the required RPM, and I found the amperage that it takes, and I matched up that amperage with different amperages of different motors. It was found that the 1500 kilovolt rating was the most adequate for the cruise motors, and the 1200 kilovolt rating was most adequate for the high lift motors.
Some of the challenges we faced when designing was capturing complex geometries such as the wing box on the wing. So certain aspects of the project we decided to additively manufacture, 3D print those parts. So when designing, when we assign materials to those certain components, they would have different weights and masses inside CAD than they would when actually 3D printed. So that posed a challenge when we went out to do the stability analysis to get accurate weights and those CG positions on the plane. Our original concept for the fuselage was designed out of foam. However, we later changed that design to be balsa wood for the feasibility of manufacturing. We made cutouts in the between the cabin and the nose of the plane, so that way we can position that battery perfectly to achieve our targeted CG. During the design phase, we took feedback from our CFD and FEA results to tweak our design to make our plane more aerodynamic. One issue we came across was our FEA analysis of the wing. The stresses were too heavy on the edge of the wing and the wing was snapping on our FEA. We had to go back and add reinforcement through our wing, and as you can see, we added an I-beam for stability. Another design feature of our project was being able to take the wing off, disconnect it from the fuselage, so that we can access the electronic components within the cabin.
For stability analysis, we had to use the resources based on our theoretical values that we captured in CAD and Fusion 360. We were able to use XFLR5 to come up with a stability analysis for the aircraft. We used the theoretical weights and the theoretical masses in our CAD programs and in Fusion 360 to put that all together to come up with a suitable dynamic and static stability analysis for the aircraft.
The assembly process mainly took place at the Innovation Lab at UCF, where a lot of things were laser cut and put together. It also took place at our lovely residence here. During the integration process, the team encountered some challenges, such as the tolerance between two parts that needed to be put together was insufficient or inaccurate based on what was predicted through CAD. Therefore, some sanding down had to happen in many of the balsa wood and also the carbon fiber rod, so to make sure it all fit together.
My name is Robert Scully. I was in charge of the controls, control surfaces, and the electronics portion. The control surfaces are important because they help with the turning of the plane, in particular the pitch, yaw, and roll. So for our control surfaces, we have 2 ailerons, 2 elevators, and a rudder. The max deflection angle for these are going to be 20 degrees. For the electronics portion, we chose the Pixhawk 5X for the flight controller. We decided to pivot away from that due to the complexity of it and the fact that it took up too much power from our battery. The battery that we chose was a 3300 milliamp per hour and 14.9 volts battery and 14.9 volts. We chose 5 servos for the 5 control surfaces that were mentioned before. The servos will actually help move the control surfaces as needed. There will be a torque of 4.1 kilograms centimeters. For ESCs, we chose the half ampere of the motors, which are going to be 40 and 15 respectively.
So as part of our testing phase, we tested each motor and we saw that the high-lift motors outperformed the requirement that was set forth at the beginning, and we also found that the cruise motors outperformed the requirement.
The skin of the entire aircraft was covered in a heat shrink wrap, which is a plastic that's cured over the entire skin, adding very good support for different skin frictions and different loads that were to be experienced throughout the section of the airplane.